Evening, everybody. So, if I have not greeted you already, tonight we are going to be looking at electrochemical reactions, which is the follow-on from our acids and bases topic. Okay, it extends all the way through. So it's still part of acids and bases. Okay, although it does. This is just one of its branches. Okay, because now we're branching into another similar type of acid-base reaction, or similar type of reaction where similar process occurs, and we're branching into redox reactions. Okay, now redox reactions in grade 10 and 12 are tested very much in the baby phase. All right, it's very watered down and quite simple. Okay, in grade 10 you learn about the transfer of electrons between substances. You learn about half reaction. You learn about which is a reduction reaction, which is an oxidation reaction, and you also learn about in grade 11 you learn a step further. You learn oxidation numbers, okay, and how oxidation numbers work and what purpose they serve. All right, as well as identifying through oxidation numbers in grade 11 if a reaction is indeed redox or not. But when we get to grade 12, which we are currently in, we actually look at real life redox reactions. Okay, and it all forms under the cloud of electrochemical reactions. So electrochemical reactions involves the chemical reactions where chemical energy is converted into electrical energy, or where electrical energy is converted into chemical energy. Okay, I'll say that again for the people at the back. Electrochemical reactions involves the chemical reactions where chemical energy is converted either into electrical energy, or where electrical energy is converted into chemical energy. Now, there are two types of cells that deal with this electrochemical reactions. Two types. The one being the galvanic or voltaic cell, and I misspelled that, by the way. Let me just correct myself. Just be L there, voltaic. All right, because there is a presence of a voltmeter. It's more commonly referred to as a galvanic cell, as well as the electrolytic cell. You may or may not have heard these two terms before. Now, what is the galvanic cell? Now, the galvanic cell, this is where chemical energy is converted into electrical energy. Okay, so we are using chemical reactions to induce or generate an electric current. Okay, that is very much possible. Okay, and that's what happens at the cell. Later on in the session, okay, I will draw the galvanic cell for you and show you how it looks. I'll give you an actual drawing, because in some exam type questions, you may be asked to complete the drawing of a galvanic cell, or you might be asked to label a galvanic cell, or you may be asked to draw it from scratch, a simplified unscaled diagram. Maybe, okay? They can ask you anything. A little bit of an extension there. The galvanic cell has self-sustaining electrode reactions. In other words, these reactions that occur within a galvanic cell, they happen simultaneously. Okay, that's what that means. Self-sustaining electrode reactions. Different reactions occur at the different electrodes. Okay, a galvanic cell has an anode and a cathode, and we will learn the difference between those two and which reactions take place at which anode or cathode. So that's the galvanic cell in a nutshell. Okay. If I scroll just a little bit downer, unfortunately I could only fit the electrolytic cell underneath the little slogan here. Doesn't matter. The electrolytic cell is the opposite of the galvanic cell. This is a cell that converts electrical energy into chemical energy. Okay, that is the main difference between the two. Okay, main difference between the two in terms of functions and functionality and the purpose that they serve, but there are some notably physical differences, that's what I was trying to get to, differences that we can see with the naked eye, that we can obviously tell which one is which apart. Okay, moving on. It's important to denote that in both cells, the galvanic and the electrolytic, the chemical reaction can be divided into two half reactions, okay, in which electron transfer does take place. Now, we should remember these terms, the oxidation half reaction as well as the reduction half reaction, okay? In each cell, these reactions occur. Okay, now the galvanic is a little bit more, I would say, a bit more straightforward to note and also see how these processes happen. Okay, so I took the liberty of constructing a bit of a table of what I think is most important to just jog the memory about oxidation and reduction, okay, which is otherwise formally known as redox reactions. Okay, so I've always learnt oxidation in green and reduction in another color for some reason. So I'm just gonna keep going with that little theme. So let's start with oxidation. Okay, now oxidation we know is loss of electrons. Sorry, before I carry on with oxidation, just to go 2 steps back, this little acronym over here, oil rig. Okay, some of us may have learned slightly different acronym, such as Leo and GER, G-E-R, but oil rig is by far the easiest because it's easier to say and make sense when I say it. So oil rig exists for us to remember the different types of reactions. So oil, oxidation is loss of electrons, okay? That's what that oil part stands for, and rig stands for reduction is gain, or is the gain of electrons. So that oil rig acronym should jog your memory. It's a great little memory tool to be able to remember the difference between oxidation and reduction. Okay, jumping back into oxidation, like I said, it is the loss of electrons. With the oxidation reaction, there is the presence of what is called a reducing agent. Okay, now what is a reducing agent? Okay, this can be a 1 mark or 2 mark question in the exam. A reducing agent, and I've summarized it for you there, although I will say the full term. Reducing agent is the substance that is oxidized. Okay, very important. Reducing agent is the substance that is oxidized. In other words, the substance that donates or loses an electron or electrons to another reactant or to another substance in the reaction. That's what the reducing agent is. So notice that a little bit of a memory battle is going to go on in your brain if you are remembering or learning this for the first time, is that we're speaking about oxidation and now we're bringing in reducing, and reducing kind of sounds like reduction. Okay? But we must not get those two mixed up. So think about this. With oxidation, reducing agent. With reduction, oxidizing agent. Okay? So that's the only two that's mixed. Okay? Otherwise, everything is oxidation, everything reduction is reduction. Okay? That's the only two things that I must point out. The next point there is that oxidation does go hand in hand with oxidation number. However, what it goes more hand in hand with is the increase. Okay, and I'm going to just write that in here. It goes hand in hand with the increase in oxidation number. Okay, so in other words, if we have a look at this example, the oxidation number of the reducing agent would increase. So this is the oxidation reaction that has occurred here. So if this is the oxidation half reaction, zinc is my reducing agent. Alright? Because it was 0, alright, and the oxidation number increased from 0 to 2. Alright? Because it is now ionized, in other words, so it takes oxidation number becomes the same as the charge on the specific atom or element. So it went from 0 to positive 2. It had an increase in oxidation number. So I know that this is my oxidation half reaction and zinc is my reducing agent. In other words, the reducing agent, it acquires a higher or more positive oxidation number with the donation of electrons, as we can clearly see. Okay, freely donates electrons. Okay. Last point there is oxidation takes place at the anode. Right, which is the anode is the one of the electrodes that exists in both cells, galvanic and electrolytic. Okay, but at the anode, we'll learn more about that as we get closer to the galvanic cell itself, but oxidation does take place always at the anode of either one of the cells. That's oxidation. Its cousin, reduction, completely the opposite. It is reduction is the gain of electrons. Okay, and in a reduction half reaction, we find what is called as the oxidizing agent. In other words, the oxidizing agent is the substance that is reduced. In other words, it accepts the electrons from the other substance or from the other reactant in the reaction. Okay. So the reduction goes hand in hand with the decrease in the oxidation number. Okay, so let's have a look here at copper. We see that the copper half reaction is a reduction half reaction where copper 2+ is being reduced to just copper. Copper 2+ is being reduced to copper 0 if we speak in oxidation numbers. So I can clearly see that there is a decrease from, let me change that to my color, sorry. There's a decrease from +2 or +2 here as my oxidation number for copper to copper 0, meaning there's a decrease in oxidation number. I know this is a reduction half reaction just by looking at it. Okay? In other words, the oxidizing agent, which is copper 2+, the substance that gets reduced, okay, it was 2+, became 0, requires or acquires a smaller or more negative oxidation number with the acceptance of the electrons. Okay, and where would the reduction half reaction take place? If oxidation takes place at the anode, then reduction will take place at the cathode. This is a very important table to get down and to remember, because this counts in your favor when we learn the cells, galvanic and electrolytic. It's very important for you to know which half reaction is which, how it is written, and where which reaction takes place at which electrode. That is going to, one, help you score much higher marks in all of the questions, and number two, it's going to help you with be more confident also to answer those questions and not get confused. Let's have a look at an example. Now this example is of grade 12 standard. Okay, so grade 12 standard, now they say I have something called aluminium powder. So let's say I have aluminium powder. Okay, so the substance I'm dealing with now is aluminium. Okay, and this is how I would approach a question. Okay, let's say I have aluminium powder, and they tell me it's added to a test tube that has, let's pick a common substance here, copper sulfate. Okay, aluminium added to a test tube with copper sulfate solution, and they tell me that a redox reaction occurs spontaneously. So you like to throw in some words like that. Anyway, now they ask me formally, use half reactions and give a net balanced equation for this reaction. Now this is more your grade 12 type questions. Okay, they say identify the half reactions, write them down, and give me a net ionic equation which is balanced for the reaction as well. Okay, so they mentioned I had aluminium powder, which is Al, and was added to copper sulfate solution. And if I break that up into ions, I should have a Cu2 plus as well as SO42 minus, okay? Because these two, they obviously make up the solution CuSO4. Okay, cool. So I identified all my atoms and ions present in my little scenario question here. Now let's identify the half reactions. Okay, well, aluminium powder was added to the solution, so I know that my half reaction, I know that copper is going to be reduced, Cu2 plus 2 electrons should go to just copper, okay, because that's going to probably form around in the solution. Okay, it's going to break away from SO4, and then aluminium is going to be oxidized. So aluminium, and if I look on my table of standard electrode reductions, okay, well, not standard electrode reductions, but I think it has a shorter name, just confirm. Standard reduction potentials, okay, there's two tables. We got table 4A and table 4B. If I look for aluminium there, aluminium actually gives away 3 and not 2, so we end up with Al3 plus 3 electrons. Alright, cool. My two half reactions, okay, I have reduction half reaction, RHA, so RHR, reduction half reaction, and this one is my oxidation half reaction, OHR. Great, identified that. A lot of people were asking, what about the sulfate? What about SO4 2 minus? Okay, well, SO4 2 minus, it's what's known as a spectator ion. Okay, spectator ion. Reason being is that no reduction and no oxidation happens with a polyatomic ion like sulfate. Okay, it watches what happens between copper and aluminium. It does nothing. Nothing happens to it.
JP.
Hold on a second. Now for the third step, what we need to do is we see we have an imbalance here in the electrons. So I'm going to take this away while I'm talking. So we have imbalance there. Okay, we have 2 electrons, which is in the reduction half reaction, and then we have 3 in the oxidation half reaction. Okay, so we do need to balance. Okay, in the third step, which I'll do in the second step line, so and step 3. So 2 and 3, I know common factor or common multiple of 2 and 3 is 6. So what I'm going to do, I'm going to times the top reaction by 3, and the bottom one I'm going to times by 2 to get 6. Okay, so what I'm actually going to end up with, okay, if I write the net half or the net reaction or the net ionic equation underneath here, if I times everything by 3, I'm going to get 3Cu2 plus. Okay, 3Cu2 plus. Okay, let me just check, and I'm going to write actually I'm going to write like this, plus 6 electrons. Okay, that's for the top half over there, and that's for everything on the left hand side. And for the bottom, I'm going to multiply everything by 2, so that's going to be plus 2Al. Okay, that's everything from the left hand side sorted. So I'm just writing everything that's for left on the left, and then I'm going to do everything that's for right on the right. Alright, cool. And then just not forget this one over here for the right hand side, times by 3, so I get 3 Cu for copper, okay, plus 2Al3 plus, that's a 3 by the way, 3 plus 6 electrons. What actually should have happened here, I just realized now, is that you would write the electrons last. So you'd first write down the substance names first and then put the electrons at the end. let me just correct that. Oh, plus 6 electrons. Okay, cool. So now we see we have fixed our little problem here. Okay. So we need to cancel everything that is the same in this case. We can see that we have 6 and 6, so they can cancel, but they don't just cancel for the sake of us getting cancel happy here and we just start scratching out things. Okay, it's still like a simultaneous equation, right? If I carry that over, I have 6 electrons minus 6 electrons, which gives me 0, because I know that I can just go and cancel it, or scratch them out, and I end up with a final net ionic equation in my fourth step over here with 3Cu2 plus 2Al. On the left hand side, that tends to 3Cu, which is copper, plus 2Al3 plus. This is what is known as a net ionic equation, and we do not include the spectator ion. Right? We do not include it because it's not part of the net ionic equation for this redox reaction, because redox only occurs in between the copper and the aluminium and not with the sulfate. It's a spectator ion. Okay? If you spectator at a football game or at a sports match, you just watch. You don't play. You don't play with. Same thing here. That's how you think about it. So what we see in front of us now is a unlabeled depiction of a galvanic cell. So what we're going to do, we're going to start labeling a few of these things, okay? And I'm going to start mentioning a few things about the components of each of what we find in a galvanic cell. First and foremost, this V over here, we should be very familiar with this. This is a voltmeter, okay? That's how it's sometimes called the voltaic cell, okay? Galvanic, okay? We have 2 electrodes. One is anode and one is cathode. The C over here is called conducting wire, okay? That's why I didn't use C at the bottom. I used K for cathode because C I used for conducting wire, okay? So anode is negative. So up here is the anode, it's negative, and this is our cathode. Cathode is positive. Okay, we know what takes place at which. We know that oxidation takes place here at the anode, so I'm just going to write oxidation. That's oxidation, and over here I'm going to write reduction, because reduction takes place at the cathode. Okay, and another thing to denote over here at the anode, okay, so let me just shift, there we go, is that the electrode mass decreases. Okay, so the substance is being oxidized, the electrode mass decreases, all right, in mass. And over here with the cathode, the opposite obviously occurs, is that the electrode mass increases. So it increases in mass. Okay, opposite to what happens at the cathode. I mean at the anode, sorry. The E over here, these blue E's, okay, they stand for electrolyte. Alright, what is an electrolyte? So I'll bring these two in over here. Electrolyte. Okay, now electrolyte is known as a saline or saline solution. Okay, known as a saline solution, which with the corresponding ion as the anode. Okay, so it's a saline solution, contains a bit of salt in it, all right, of some sort. Okay, which is known as a electrolyte, and it contains exactly what they said now, the same corresponding ions as the anode. Okay, so let me just fill that in quickly. The next thing we have is the S over here, which is known as the salt bridge. Let me just make the bridge a little clearer. There we go. It's known as the salt bridge. And what happens with the salt bridge, it allows to flow anions, okay, and also cations. Okay, what happens within the salt bridge? Okay, anions and cations are allowed to flow obviously through the salt bridge. Okay, now what is the function, of course, of a salt bridge? One, it does separate the electrolytes, and the most important part of a salt bridge is that the salt bridge completes the circuit. If you don't have a salt bridge in your galvanic cell, your circuit is incomplete, because anions and cations don't have a path to pass through in order to restore neutrality. Okay, so that's why the salt bridge is a very important component of the galvanic cell. In fact, it is one of the most important characteristics. How we can identify the difference between a electrolytic and a galvanic cell, or a galvanic cell in general, is if we see the presence of a salt bridge, then we know we are looking at a galvanic cell. Of course, we know cations, anions, they are negative ions, and cations are your positive ions. And so your cations will flow through the salt bridge to your cathode, while your anions will flow from your, through the salt bridge to, of course, the anode. Thus, your voltmeter will pick up a reading. It will pick up an electrical current being induced, and that's why we know that as a result of two chemical reactions taking place, we know that chemical energy or chemical potential energy is indeed converted into electrical potential energy, because the voltmeter picks up a reading. Just a correction on the diagram. The salt bridge does need to go all the way into the solution, so I do apologize for that. Let me just extend the salt bridge a little bit. Okay, and then otherwise the drawing is 100% correct otherwise. Thank you so much, grade 12s, for joining me today on electrochemical reactions, where we covered just a little bit on the galvanic cell, as well as some redox reactions that take place at each one of the respective electrodes within a galvanic cell. This was the official introductory lesson. The next lesson we will go and dive more in depth and look at a couple of questions and a couple of examples with regards to the galvanic cell, and touch on the electrolytic cell as well.